let's make a start. So my name is Matt Warren. You probably already know that because it's written on the screen. I should say I work for Raygun, hence the literally the Raygun on my t-shirt. I have a whole bunch of Raygun swag to give away, so if you like t-shirts, a little press-out wooden Rayguns you can build and anything else, come and chat to me afterwards. Raygun do error reporting tools, analytic tools, APM tools, that type of thing, so come and chat to me if that's what you're interested in, want to find out a bit more. This talk is titled From .NET Run to Hello World. I had a very weird experience this morning in Scott Hanselman's keynote where he did the exact same demo that I'm going to do later on. I'll keep you guessing which one of his 35 demos or whatever it was he did is the one that I'm going to do, but yes, bizarre experience anyway. I should say up front that I love .NET internals for the recording, not maybe in the same way that I love my wife and children, but to me this stuff is fascinating. And maybe that's something that rings true with people here. This is not going to be one of those talks where you make some notes, go back to work on Monday, and then in your daily job you're going to be starting to use some of the stuff I'm talking about here. I want to just make that clear up front, I guess. This is very much a sort of informational talk. There may be times over the next year or so where something that in this talk rings true to you and you think, okay, that could maybe explain what's going on here. If that happens, let me know. I'd love to hear the times when this talk is that sort of thing. But this is very much, here's what's going on under the hood. Here's what's happening in the .NET runtime. I like digging into this stuff. I think other people do as well. People always get comments on when I write blog posts about it. People seem to want to come to talks to listen about it as well. But it's very much an informational thing. I think that's okay. I think that's fine to learn about this stuff. I think it's good that actually as .NET engineers running on the .NET runtime, if that's what most of us here are, that we want to have some understanding of this runtime underneath. It's generally, we can treat it as a black box. It does its thing. We give it our code, it runs it, and stuff happens. But I think sometimes we run up against that. Maybe another way to think about it is actually we should be looking to understand one level below our usual abstraction. Now, I'm not going to argue that every time you're coding, your one level below your usual abstraction is deep into the internals of the .NET runtime. We don't run into that all the time. You might be up in, say, MVC, ASP.NET land, and that time your abstraction is the ASP.NET runtime. And then we have the base class library underneath that. But who's ever used Reflector to look into some code? It's open source now, it's a bit different. But before that, you'd look into some code, and you'd be looking into, say, the base class library. And then you come up against an internal call. Has everyone ever come across that? So basically, that's it saying, we can't give you any more. At that point, that code is implemented somewhere else. And that somewhere else is generally, or always actually in these cases, will be the .NET runtime. So we have a bunch of stuff in the base class libraries written in C#. We can look at Reflector, use Reflector or other tools to look at that, .peek and things like that. But once we get below that, we're into the world of C, C++, and what's in the runtime. And that's what those internal calls are. There'll be a method with that name inside the runtime. And actually now, because it's all open source, you can go onto the .NET github.com/.net/core CLR is where the CLR open source version is kept. And you could search for that method, and you'd find that method name in there. So I think there's something in understanding our one level below our usual abstractions. As I said, I'm not going to argue that that's day in, day out. We need to do that, but there's times we come up against it. I think another reason, actually, why knowing about internals is good is if you want to write high-performance code in .NET. When Scott Hanselman in his talk this morning talked about the Tech Empower benchmarks. And if you go on to again, it's all open source, you go on and look on the ASP.NET repository, and you can see the source code for the Kestrel web server. That is the one that's being used in those Tech Empower benchmarks. And a guy called Ben Adams has done a lot of performance work, and some other people from Microsoft as well. And if you follow some of that code in there, it's not the C# code you would write. Not by accident anyway. It's highly tuned C# code. It starts to look a little bit more like C++ code. There's like bit shifting going on, there's unsafe, there's all sorts of stuff. But to write that sort of code, you need to understand the runtime. You don't write that code by accident. That's built up with years of knowledge. It's understanding what the GC's doing, what the jitter's doing, how they interact, what's going on in the runtime, those sorts of things. So I think that's one clear, concrete time when actually an understanding of the runtime is useful, aside from just, we all like to learn this stuff. So let's start off with a bit of a demo. I'm not very good at doing live demos, so I've got my notes to make sure I don't get this wrong. Let's see if I can get this right. .NET Let's run. Yes, there we go. That is simultaneously the least impressive demo you'll see all day, aside from Scott Hanson did the same one this morning. But hopefully, by the end of this talk, I'll convince you that actually that's quite impressive. We do that, maybe not every single day, but we do that quite a lot. We spin up a new console app, we try things out. Maybe now that there's the nice new command line tooling, you've tried it out from the command line, whatever way we do it. We run a .NET application maybe many times a day when we're developing. And even just what happens between when I type .NET run and hello world there's a lot going on, aside from even if we had a proper application that went on and did a bit more. And that's what we're going to talk through in the next 40 minutes or so. To give an outline of where we're going to look at the main components that make up a runtime. I think it's helpful to see what's in there and see what, particularly around the naming and stuff. How the runtime gets hosted, how the runtime initializes itself, the type loader. We just write, class foo, and then ignore it basically and expect it to get on with it and do it for us. But there's quite a lot of work that goes in to make that possible so that types can be available at runtime, they can have type safety, Jit compilation, and then everything else at the end. So onto the main components. Well, if you were to go onto the core CLR repository, this is probably about 5 or 6 months out of date, so the numbers may have gone up or down. But anyway, there's around 2.5 million lines of source code in there, 8.2 million lines of test code. There's a lot of tests, not surprisingly, when you're testing a runtime. And that's just testing the runtime. There's a whole other lot of tests that would test the base class libraries. We're just talking about tests that exercise something in the runtime, loading types, and some of the other stuff that we'll talk about in this talk that consider just the runtime. The base class libraries, in terms of terminology, is referred to as core FX, and we're talking about core CLR, which is purely the runtime. There is some C# code in the runtime, and we'll come on to where that lives in a moment. Most of it is in test code, but there is actually some in the runtime itself. But by far, the bulk of the runtime is C and C++. There's a lot of IL. Again, that's testing. When you want to test this sort of stuff out, they don't want to be dependent on the compiler. They want to give it invalid IL, for instance, and see what the runtime does with it. They want to give it IL that's structured in a certain way. So a lot of testing is easier to do with IL. There's a bunch of assembler codes. Not surprisingly, the runtime now runs on 4 or 5 different CPUs, ARM, AMD 64, x86, and so on. So specific parts of it have to be handwritten assembly. There's a bit of Python and Perl, which is, as far as I can tell, build scripts. There's nothing in the actual runtime that makes that up. But maybe pictures is a bit easier to understand. This is a heat map. The size of the square is just the number of lines of code in that particular component. And these components are the top-level folders, if you were to download the code. They're also, terminology-wise, they're the way those parts of the runtime are referred to. So if you go onto the issues or the pull requests on the repository, and now you'll see that they're labeled, and they're often labeled with one of these names. So we'll go through in a minute. We're going to get to the top left, the huge red one, because that's everything left over when I've talked about the rest. So we'll come to that last. So we'll start with MS Core Lib. This is the C# code that lives in the runtime. It's, as of the next version of .NET, it's been renamed to system.private.corelib because MS Core Lib is sort of more from the older .NET framework. They've renamed it for .NET Core going forward. But this is what sort of code you can find in there is things like reflection lives in there. The types that we expect, system.string, system.int, those sorts of things, system.object lives in there. The basic rule of the runtime is it has to be self-contained. It can't have a dependency on something else. It can't have a dependency on the base class library. It's just one of the fundamental rules of the runtime. So anything the runtime needs to do its work has to live in the runtime. But we obviously have the nicely layered base class libraries. So all the stuff we kind of generally use day in, day out, system.collections, a lot of that lives elsewhere. But stuff that's tightly integrated to the runtime is another thing that has to live in here. So system.string, system.array, they're fundamental types that the runtime knows about more than anything else. They're not purely just written in C# code. There's some C++ code that mirrors them and stuff going on. The JIT knows about them intimately so it can emit efficient code for them, things like that. So that's kind of some of the rules around what lives in the runtime. as far as possible, they want to put more stuff outside in CoreFX because that can be then shared. And if you're in, Scott Hantsman's talk about this idea of all these different runtimes that sit underneath the base class libraries CoreFX, that's why it makes more sense to put things in CoreFX. And for instance, Mono is starting to share more of the CoreFX code, other runtimes. So the idea is that the runtime keeps it as small as possible, but there is some rules in that it can't have a dependency on anything else. That's the C# code. This is the Jit just-in-time compiler. A huge chunk. I was a bit surprised at quite how much code goes into that, but I suppose it makes sense. It's got a fairly complex job of turning the IL code that we give it. You know, we compile our code with Roslyn or Visual Studio VS Code, however we compile our code. That ends up as IL code. And at runtime, that's just-in-time compiled if we're talking about the most common scenarios. And the jitter has to do a lot of things, really. One of it has to worry about different CPU architectures. It's got to emit different code. We're talking about emitting assembly, well, bytecode, basically, native code for the runtime. So it has to worry about that. It has to worry about performance. It has to worry about correctness. You know, we expect our code, when we're accessing arrays, for instance, we expect the code to not go out of bounds. There's things like that it has to worry about. It has to worry about emitting code that's going to do exception handling. A lot of quite low-level stuff the JIT has to worry about. And on top of all of that, in the common scenario, it's just in time, as in that we can't call the method for the first time until the code has been jitted. So it has to be fast, because if it takes too long, it's not like a C++ compiler where you can compile it once and then that's native code. It does this at runtime. And we get onto the JIT at the end and some of the tricks it uses, but it's trying to do this balance between making the most efficient code but not taking too long, hence why there's a lot of code in there. The GC is a fun one. Does anyone want to guess how big the gc.cpp file is? It's the main file that makes up the biggest, the core of the GC. Anyone want to have a guess at how many lines of code it is? 1,000. 22,000. That's closer. 22,000. Still higher. Any more guesses? Okay, I'll put you out your misery. If we look, we can actually look now that it's. So it's so huge that the tooling that I've got really doesn't like it, but it is 37,300 lines long. And you sort of saw it a bit there as I was going through it. It's a whole lot of if-defs as well. Basically, it's a single file that is all the versions of the GC. So it's server GC, workstation GC, background GC, foreground GC, multi-CPU GC, single CPU GC. And what it means is this file can then be dropped into other .NET runtimes. So as far as I know, it's mostly the same GC in the .NET Framework and .NET Core. They can just toggle some if-defs, basically, if they want to have it behave differently. Again, for the .NET Compact Framework and things like that. So, and going right back, fun fact, the GC was originally written in Lisp, and they used a tool to transpile it into C++. And they don't do that now, but that was how the very first version. There's a blog page out there about the guy who wrote the very first version of the .NET GC. I don't know if I'd like to be a dev working on a 37,000 line code file, but I think that by this point, if you can still do it after there's one main developer who's a .NET GC developer, and she's a lady called Mauni Stevens, and she's been working on the .NET Runtime for a long time. And I guess if she isn't fed up with working like this, then it's going to stay like this. People have opened an issue. You can search for it on the GitHub repository of why is this one single file, could it be refactored, and you can search for that and read up why. But that's the bulk of that GC. The GC, like the JIT, is sort of relatively standalone. They have an interface, they talk to the rest of the runtime, but they can operate on their own thing. The runtime calls into them, and they call back into the bulk of the rest of the runtime, which is the red block, through an interface, but they can stand alone. And in fact, there's actually a sample in the repository where you can use that GC outside of the .NET runtime. There's a fairly simple sample showing actually here's the GC can be used that way. And there's also the reverse of that. There's work being done where you can provide an alternative GC to the .NET runtime if you really want to do that. There's an interface you have to implement, and then you can do the work. And there's a guy called Conrad, I forget his surname, but he's just written a .NET GC book called .NET Memory Management. It's 1,000 pages long, which shows you how much is in the GC. But on his blog, he's talked about the alternative GC and what's done there, so that's worth looking up if GC is more of your thing. garbage collection. These two blocks here are purely to do with debugging. It's what the runtime provides so that we can debug. So SOS, who's heard of SOS, Son of Strike? Yeah, a few of you must. So if you're debugging .NET in WinDBG, you must know the magic commands .load by SOS CLR, that's the SOS here. And what it is providing is a view of your .NET process. WinDBG only knows about native, not managed code, basically. And SOS provides commands like, give me a list of all the .NET threads, runtime threads. Give me a list of the call stack. Give me the method at this location. Give me the IL of the method or the assembly code of the method. Those sorts of things, that's what it provides. And it has to map between those two worlds, so there's quite a lot going on there. And the other part of that is the purple one at the top. DAC is the main, it's called a data access component, and that's purely providing, if you imagine you have your .NET process as a chunk of memory, the DAC is like a view on top of that, and it allows it to call in. And so that chunk of memory is, a large amount of it is data structures that the runtime keeps. So there's a data structure in the runtime, which is the list of all the threads. There's a data structure in the runtime for every class that you load, for every method. And the DAC is a way to say, give me those information about those data structures from this process, either a memory dump or a live process. So we pretty much take it for granted. We hit F5 and we're F10 stepping through or whatever it is. And obviously, if we're doing that in Visual Studio or VS Code, that end of it is providing a lot of that functionality, but quite a lot of functionality is also provided by the runtime to make it debuggerable, is that even a word? To make it easy for us to debug it, to make it easy for us to inspect those processes. And without this sort of stuff, we wouldn't get very far debugging our code, which is handy. The PAL is just a small thing on the side. The idea of this is, you might have heard of this from, say, Windows and things like that. It's the platform abstraction layer. And the idea is this is the part of the runtime that is dealing with different OSs. So now that we have .NET Core running on Linux, Unix, different flavors, Mac OS, and obviously Windows as well. The idea is that the abstraction of those bits is in one place, and the rest of the runtime can just call methods that might call out to the OS, and this part handles that. And then ink in the middle is really a whole bunch of header files and interfaces of the different, how the different components. So for instance, there's one in there which is the GC to EE, which is the top left execution engine. There's an interface of those two talk to each other, and vice versa when the EE talks back to the GC. The same for the EE and the JIT and backwards. But also, some of these are external ones. So anyone here work on sort of third-party tools using the .NET debugging APIs, profiling APIs? Anyone? Okay, well, you're using those tools if you're not working on them. Any third-party debugger, any tool like Rider that provides a debugging experience in .NET, any third-party tools like the one I work for, Raygun, but other tools that provide APM or diagnostics experience would probably be using some of these APIs. There's a whole range of APIs the runtime provides for people who want to write. Unfortunately, almost all those APIs are, you have to access them from C and C++. They're not APIs for managed code, but they do mean that we can have an ecosystem of tooling around this, and there's a stable API provided there, and the tool writers can rely on that. And the VM then is basically everything else. And it's got bits per CPU assembly code in there. But what's actually contained in there? Well, there's a whole lot of things. The type system, as I said, we just write some code, but the runtime needs to know that. It reads it in, as it loads our DLLs, it will read it into its own data structure, and it has to do that for a few reasons. One is because it needs to work with them itself, but another one is because of reflection. When you use reflection, it has to have that information available so that it can say, right, yes, that type you're asking me for has this fields, or has these properties, has these methods, and that's some of the data structures it keeps in there. And generics as well are worth a special mention. We probably quite like using generics, but there's a whole lot of work went in across the whole runtime to make generics possible, because generics in .NET was done in a way where it was done, I guess, in a pure or Java took a different route, should we say, with generics. We have generics baked into the runtime, real generics, if you like, and there's a lot of work that was done to make that possible. All the built-in types are in the VM as well. Loading of types and classes, threading, the abstraction of threading, and I'm not even talking about when you get up to the level of thread pool and stuff like that, which lives actually outside of the runtime, but just the raw .NET threads are an abstraction on top of OS threads. Exception handling and stack walking. We probably take these for granted or don't like them, because anytime we see an exception, maybe we're tasked with figuring out why it's happening in our code. But we probably wouldn't want to do that if we didn't have a nice stack trace. And we could probably be quite grateful that the runtime provides that. If you've ever done any work in C or C++ or other runtimes that don't give you that nice stack reporting. But again, a lot of work has to take place to make that happen. It's not straightforward. Event tracing and profiling. Anyone heard of ETW, event tracing for Windows? A few people. And anyone else heard of a tool called PerfView? A few more people. Okay, we're going to get into that in a moment. But anyway, there's some tools that will let you collect events that the runtime itself emits. And in ETW events are obviously across all of the Windows OS, but the ones that the .NET runtime emits are things like GC events happening, allocations happening, jitting. So sort of the runtime's telling you something's happening in the runtime. And you can use PerfView, or you can actually write code with libraries from NuGet that let you capture those events and you can analyze them to see what's going on. And then p-invoke. .NET has quite a nice story of calling out to native code. If anyone had ever put, DLL, import attribute and that sort of stuff, there's quite a lot of work to make that happen. It has to make sure that the data from .NET gets put into the right format that the native code expects, and then when that comes back, the vice versa. Has to make sure that any exceptions that happen in native code are turned into .NET exceptions and things like that. There's quite a lot of work going on there just in p-invoke. So that's the virtual machine. So when I ran that demo before, I typed .NET run. There's various other ways you can do .NET exec, execute, but all of those ultimately end up calling into something called the Hosting API. And that's because our .NET code is not native code. So something has to initialize the runtime, and then the runtime has to run our code, right? Unless we're talking about ahead of time compilation in .NET, so you have that in a mono a bit, and then something called core RT in the .NET core world side of things. Unless we're talking about it ahead of time compilation, our code that we give the runtime is not native code. So it has to, something has to start up the runtime. If anyone played around with the new tooling where you can do .NET Publish and those sorts of things, people familiar with that? So that's a way to get more self-contained apps, the folder with the entire runtime. And if you notice in there, when you publish your application, you'll have your myapp.dll and you'll have myapp.exe. Myapp.exe is basically a wrapper that calls into the Hosting API, initializes a runtime and says, I'd like you to run myapp.dll, find its main entry point or whatever it might be. There's a few steps it goes through. This is one of the APIs that lives in that diagram I talked about before. I'm not going to go through it all because there's quite a nice MSDN docs, but maybe the interesting bit is actually that app domains are still a thing in .NET Core. So one of the things that went away with .NET Core was the ability to create app domains. We can no longer use app domains as a process of isolation. They've sort of said that's not a real thing, in terms of that's not real isolation. That's not really fit for purpose. If you want isolation, run multiple processes. App domains are no longer the way to have that. But there's still one app domain living in the runtime and the Hosting API. Maybe that will go away eventually, but it's tied into this API, so probably it'll break too much stuff. It now lives on a sort of a historical thing. I think there's almost no method you can call on system.appdomain left anyway. You certainly can't spin up new app domains. There is a new mechanism called application contexts if you want some of the isolation app domains give you in terms of loading plugins and things like that. But in .NET Core, app domains don't live except behind the scenes. But it goes through these steps. But let's see it in action. So this is the code from that web page. I'm not going to talk you through it all because you probably didn't come here to see C++ code. It talks through the steps, but let's see it in action. So we're just going to run up the host and ask it to execute a DLL. And the benefit of obviously this all being open source is you can put your own crazy ASCII text in and pretend that you made your own version of the CLR. But the point is it's running through a load of things. It's setting up the application path. You can sort of see net core app. It's initializing it. This is roughly what happens when you type .NET run, the same sort of steps it goes through. Really what it's doing is collecting up all the assemblies that are considered part of the runtime, so all the DLLs, system all the ones that live in the base class library. In the .NET Core world, most of those come via NuGet packages, and if you store Scott Hanselman's talk this morning, they live under that folder where you can have different versions side by side. So this hosting API here is the simple one. It's really, look, here's a folder with a load of DLLs, and here's my main DLL I'd like to run, do it. In the world of .NET Run, it's doing a lot more behind the scenes. It's deciding which runtime you want to use. It knows about .NET Standard, .NET Core App. But at the bulk of it, at the bottom of it all, it's really, here's some DLLs that you're going to need. Here's the main DLL. Go and run the runtime. And at the end of it, we get nice hello world as before. So we've seen how the runtime gets initialized. The next thing we've seen how the runtime gets hosted. The next thing it does is it has to initialize itself. There's a whole lot of stuff that goes on. If you've ever heard people say .NET looks bad in sort of small hello world benchmarks, it's because the runtime is doing quite a lot of initialization with the expectation that you're going to do more than print hello world. It's getting stuff ready for your application to run for a bit longer than that. So if you do if you time the time it takes for a .NET app to start up, print hello world, and exit, it's going to look bad compared to a C++ app. That's because there's a whole lot of stuff that's gone on there, and you've just kind of wasted all that. You've asked the runtime to start up, and then you've gone away and done nothing useful with it. But some of the things it does. So it needs to set itself up. It has a whole lot of low-level components. If you're really keen, because I counted it, you can read the 68 things the CLR does before executing a line of your code, and we'll look at that. But in effect, there's one method in the runtime that initializes all its subcomponents. A lot of the stuff we saw in that diagram earlier. Initializes things, it starts up things like error handling. Obviously, the runtime has its own error handling if the runtime goes wrong. Has anyone ever seen fatal engine execution exception? I think it's something like that. You're doing well if you get those sorts of things. That's basically the runtime saying, I don't know, something's gone horribly wrong. So the fact you don't see that very often means that the runtime, it has its own error handling, exception handling built in, and it does a better job so that you get things like Stack Overflow exceptions or out-of-memory exceptions, those sorts of things. But they're being converted from something happening in native code. By the time we see them, they're coming up as managed exceptions. Even though you might not be profiling or debugging, it needs to get ready for instance, a debugger to attach at a later time. So there's things that's being spun up there. GC needs to get ready so that by the time your code starts executing, you can start allocating. So it needs to initialize itself, app domains if applicable. Yeah, there's a whole load of things. Just to show it in code, to see, this is the let's boom bump that. This is the function that it runs through, and you can just see initializing the JIT, initializing the power layer, initializing the debugger, initializing exception handling, and so on, setting up threading. Stubs will come to at the end what that's going on there, but there's something the the runtime uses quite widely. Garbage collecting, blah, blah. Anyway, the point is there's a lot going on. That's the point I want to make more than exactly all the specifics. But if you really want to look up the EE helper function that runs it up, you can again, because it's all open source, you can go and take a look. At the end of all that, the runtime initializes itself. It's then ready to go. It's then ready to start executing our code. But let's look at that in a slightly different way. So a few of you said you'd heard of PerfView before. That's good. I kind of make it my aim to tell more people about PerfView. PerfView has a slightly bad rap, as you'll see in a minute. Is when you load up PerfView, it looks like this. And there's no point in me trying to even zoom in, really, because it's not going to, it's interesting UI-wise. But I always argue with PerfView that I would rather have a very powerful tool that looked horrendous than a very pretty tool that did nothing useful. And PerfView is very much at that end of the scale. There's a lot of powerful, low-level information you can get out of PerfView. It does take a little bit of digging around. It does take a little bit of getting used to. It has got a bit better since it's open source as well, so people have been community contributions and sending that. As far as I know, a lot of the Microsoft teams themselves use PerfView for diagnosing performance issues particularly. You can certainly go on the repositories and see people posting screenshots from PerfView. There's a few things it will give you. We're going to look at CPU sampling in a moment to see what the runtime does during startup. You can use that for your own code, so it's a sampling profiler where it takes a snapshot of the call stack once every millisecond, and at the end of that you can see where the most time is spent. It will also tell you about memory allocations. That can be native ones, as in what the .NET runtime is doing, but more importantly for us, I guess, is we can see .NET allocations where our code's allocated. A lot of this is also available in third-party tools, I should say. So a lot of the third-party profiling tools can get you similar information. PerfView is just another way of getting it. It also hooks into ETW events. But let's, I'm going to show you the, if you thought that first screen was interesting, this one. No nice responsive UI here, eh? It's, but we're just going to run a, the main one is we're going to run with CPU samples turned on. If anyone knows what all of these tick boxes do, please come and tell me afterwards, because every time I look at it, I get more confused and there's new ones pop up. There's 3 that have the word .NET and alloc for allocations in, and I always get confused which one's which. But anyway, you basically give it an application, you give it a command line, and you run a command. And then it does some very weird things with Windows, and has a nice. You can tell it's low level because this is the progress report you get. This is the yeah. Anyway, it's going to go away and do its thing. It's collecting ETW events coming out of the .NET runtime. That's what it's doing there. PerfView. So those raw events are relatively easy to collect. What PerfView does on top of that is builds a whole lot of intelligence. So it collects, for instance, if we're talking about GC allocations, it will collect the raw events, but it will analyze those and say, actually, these represent GC pauses. And GC pauses are significant because in a lot of situations, when there's a GC pause, that's the GC running and not your code running. And that can be a performance issue. So it does some work there. So it's, yeah, it's done all that. So we then get a nice data file. Yes. And this is the first screen. I think if you've done PerfView, if you tried out PerfView, you've got to this screen and you see this and this sort of stuff. At this point, you probably give up. It is a bit cryptic, but what it's really telling you is how long is spent in each method, exclusively, as in just that method, and inclusively, including its children. But fortunately, they've recently, well, an open source contribution built something called flame graphs. Unfortunately, they don't really, they don't really demo nicely. So I'll show you in a different way in a second. But flame graphs, as an aside, has anyone heard of flame graphs before I just mentioned them? Good, a few people, but a few going to learn. Roughly what flame graphs give you is a way of analyzing, well, in this case, we're talking about CPU samples, so it's where time was spent. The main thing to remember is it's not over time. This is taking all the samples, so I think I ran that program there for 10 seconds. It collected CPU samples once every millisecond. At the end of it, it puts them all together. So what's on the left of the flame graph isn't what happened first and then on the right. The left to right order is almost arbitrary. But what it is the wider the block, the more time was spent in that function. So obviously in a lot of call stacks, there's common functions, So at the bottom, we generally have main. Everything starts in main, right? 100% of the time is spent in main. But that's not very useful because nothing useful was done in main. It was the functions it's called. What you're looking generally for flame graphs is a function that's flat because it doesn't have any children. That means actually 20% of our time was just spent in this case, the byte function, right? Teeth is a lot of time, but most of the time is not in teeth itself, but it's in its children. So that's the thing to look out for. Alligator and panda are useful because they're the 2 main functions, but not very much time is spent in them individually. It's stuff after them. As a very quick aside, if you haven't checked out or not heard of Julia Evans, and her blog is jvns.ca, or she's known as @Bork on Twitter. She makes these fantastic zines explaining quite complex technical things in this sort of way. There's loads of them. This is one she's done on flame graphs. There's other ones on processes, on like low-level stuff, but explained in a really engaging way. So hopefully that's given you an idea, if you haven't before, on what flame graphs do and what they look like. Let's have a look. So in sort of Blue Peter style, here's one I prepared earlier because unless I clean it up and make it on a slide, it's impossible to see what's going on in PerfView. But the point is, we're seeing larger sections, but even still, I know you're not going to be able to see that. So anyway, this is what it looks like if it's annotated. And this is where the runtime spent its time in that Hello World application until it called our code. So you see a whole chunk of the time is actually jitting and running the actual code itself, because when you first call the main method, that then has to call, it has to then, at some point, it has to then jit the console.writeLine method, for instance. And sometimes there's methods called behind the scenes that we don't explicitly call in our code. So there's a bit of time spent in jitting there. System.app domain setup is roughly the managed code setup, and then EE startup is the 68 steps that I talked you through in the previous slide. That's what's going on there. That's things starting up there. So yeah, that's what in terms of time spent. Sorry, that's where it's spent, and that's why I think in this one of these thin bars here is actually executing program.main. I forget what it is, but anyway, this is why we say like Hello World benchmarks. You know, very little of this time is spent in executing our code. Right? There's all the other stuff that goes around it. Obviously, you only pay that jitting cost once, but if you're just printing Hello World to the screen and exiting, you're doing all that work to not get it reused. As I said before, it's not like left to right, so this actually happens first, and then this one finally, but it arranges it differently. It's over, this is the whole sample. So that gives you an idea of what it looks like in time spent. Fun thing with this, so I used this before and I tweeted this out, and it happens that one of the runtime engineers follows me on Twitter, and realized from the screenshot and another one, a larger one I tweeted, that actually there's some stuff happening in a kind of Hello World application that shouldn't be happening. Because in terms of the runtime, they're quite, they take quite a good look at actually what the runtime does before our code can execute. In this kind of world of microservices and where we're spinning up things a lot more, the time to our code being executed is important, right? You know, the time, that often means the time to first request, right? We've seen those scenarios where the first request takes a long time. They do what they can in the runtime to make sure the runtime gets out of the way. It only initializes what it has to. And I can't take much credit. I stumbled across this by accident. I didn't even know I was seeing a problem, but I tweeted it more out of interest. But they saw it and basically said they were doing stuff in that process that shouldn't have been done. They were doing stuff that didn't need to be done before the user's code was executed. That could have been done afterwards, like asynchronously in the background type thing. And so as of .NET 3, they fixed that. And it's around something called event pipe controllers, and it's a diagnostic thing. But the point of that is to actually, they do look at this sort of stuff. It's important to them. How many methods are jitted before your code is? How many methods are automatically jitted even if you don't call them? Those sorts of things. How many things the runtime does. They try to make sure it does the bare minimum because they realize, and particularly going forward with containers and Docker and all this sort of stuff, this thing is more of an issue. The other main thing the runtime does is allocate a bunch of memory, and that's pretty much all, the bulk of it, is for the GC. So the runtime itself allocates a whole load of memory that it uses, but that's kind of a bit hidden from us, and we can't really do much about that. The runtime does that. The bit that we can control is what the GCs do, because if we're allocating lots of memory in our code, or lots of objects that need lots of memory in our code, then the GC has to do a bit more work. But the GC pre-allocates a bunch of memory up front, so it's got the heaps ready to go, so that when you want an allocation, it has the memory already pre-allocated. That varies across workstation, server, 32-bit, 64-bit. It's also quite smart with reserving memory versus actually paging it in and that sort of thing. It works, in a smart way with the OS. So you won't necessarily see these in the kind of headline figure if you look in Task Manager or whatever, but it's doing that. But it's getting to the state where the first time you new up an object or allocate some memory, it's got a chunk of memory that it can give you, a section of that memory ready to go. And then later on it does its work of cleaning up that memory, and it tries to reuse memory intelligently as well. So we've seen the runtime being initialized externally. We've seen the runtime initializing itself internally, if you like. We've seen where it spends its time doing that, some of the main components. And now onto the type loader. We just write, as I said a few times, we just write our types. But there's a kind of fundamental thing that we expect, is that type safety, isn't it? There's certain rules. You know that if you write code like this, you're going to get a compiler error because you're trying to new up an abstract class, right? The same if you tried to new up an interface or whatever, or if you tried to access a private field of a method. Reflection is different if you're using that. That's a different mechanism, but certainly in regular code, if you try to access private fields, there's certain rules. You can't have multiple inheritance. All these sorts of things the type system provides us. .NET is a strongly typed language. The runtime has to care about that as well, because what the runtime can't do is just rely on all our code coming from a nice compiler. So you use Visual Studio, VS Code, whatever. It won't let you write code like this, or it will refuse to compile code like this. It'll give you an error and it won't compile it. There's nothing to stop you if you saw, again, actually in Scott Hanselman's talk this morning, there's nothing to stop you using the IL DASM tool to disassemble from a DLL into the raw IL. You can edit that, and then you can use IL ASM to assemble it back. And it does virtually no type system checks. It will check on the syntax of the IL, but that's about it. And actually, there's a reason, because they want that tool to be able to write invalid IL so that they can test it in the runtime. If there's no way to create these sorts of scenarios, they couldn't test it. The main point is the runtime has to do its own checks. It can't just assume all this code has come from a nice compiler. There's various different ways. You can even edit the binary yourself if you get that far. But the point is it has to do these checks itself at runtime. So when it's doing the type loads, it needs to check for these things. Are you trying to access a class you shouldn't? Are you breaking class hierarchies? Whatever it might be. The runtime has to pretty much mirror all the checks that the compiler would do. But it does them in terms of throwing a type load exception. It doesn't give you a nice error message saying the line of code to fix. It just says type load exception, you can't do this, or whatever it might be. But it gets a bit more complicated. Does anyone want to admit they've ever written code like this? The main point is, and after having looked about it quite a lot of times, I'm not a compiler or a language person. The main point is class A is dependent on class B, and class B is dependent on class A. You've got a recursive, mutual, whatever the right word is, but it's at the type level. It's not at runtime. They're trying to, so the point to remember is class B shouldn't load if class A is broken, and class A shouldn't load if class B is broken. But which one do you do first? It's like chicken and egg. So either they have to both be okay and they both have to load, or if one of them's broken, neither of them can load, because at that point the types don't make sense. You break type safety, all this sort of stuff. And it mostly comes in with generics. It's hard to do this sort of crazy recursive stuff at a type level without generics, but yeah. If anyone could come up to me afterwards and say what you could replace A, B, and C with real names to make this a real life proper scenario, I'd love to hear of where you could actually justify writing code like this. But anyway, it's possible to write it. So what the type system does when it's loading is it loads everything in stages. It starts with the class just loaded as raw data, and then it works through. And you can see things like it's looking at the parents of the class, exact parents, and its dependencies. And it basically goes through. So in those cases, we have two classes that depend. And it will move through all the types to each level. So it will get all types to level 1, then all types to level 2, all types to level 3. And then it knows, for instance, it knows that this type can't move to load its dependencies because one of its dependencies is broken. So this type, type A couldn't progress past this stage because type B hasn't got to this stage, that sort of thing. So every type has to, dependent types have to move up at the same level. And then once you get to the end, once all the dependencies are loaded, you know that dependencies are loaded, so you know that you're okay because your dependencies are all okay. They wouldn't have got to that stage if they weren't themselves okay, and so on. And it's a bit like the way transactions are committed in a database. You know, everything sort of moves up in steps, and at the end it says, right, is everyone happy? And it does the final step at the end, which is basically flipping a bit, saying, right, we've got this far, there's been no errors, okay, everything's good. We can say the types are okay. It's a very simplified version of what it's doing, but it works through these stages. So we finally got to the point our code will actually run. That's the thing. All of this is before any of our codes run. If we leave aside static initializers, which are a slightly different side of thing, but in our Hello World example, all this would have happened before anything in our code would have run. And we have Jit Compilation, as I've talked about before, in .NET, and it works a bit like this. The point of what it's trying to do is that it doesn't want to JIT a method until you actually call it, right? So it could, as every single type was loaded at the beginning, it could say, right, this type's got 5 methods, I'm going to JIT them, 1, 2, 3, 4, 5. But that would waste a lot of time if you never called those methods, or those methods didn't get called till later. So what the runtime does is when it emits a method, it actually emits, it has a temporary entry point, but it goes through a series of stubs. And stubs, the simplest way to think about those is like a few instructions of assembly. They're not a full method call, and they just do a bit of housekeeping. So the first time when you try to call a method, it comes through this route. It starts off at the temporary entry point because that's where it knows the method is, and it gets the pre-code fix up, the pre-stub, and the pre-stub worker is basically the bit that calls the JIT. So the first time it calls a method, it gets pushed through these series of stubs, and it ends up having the method JITted. Afterwards, when it's been JITted, it's done a few extra things. So we've lost the pre-stub now. It's lost that level of indirection. That's gone off. And what it's done is it's rewritten, in effect, this fix-up to now point directly to the native code via this stub. And when I say rewritten, we're talking about assembly instructions being changed, an address, in effect. And that pre-code fix-up will be something like, use this address and jump to it. And what it would have done is between the first and second time, that address will have changed. So the first time it jumps to the pre-stub, the second time it jumps to the native code. It's also built this stable entry point, and that is, so that point onwards, the rest of the runtime knows that anytime you want to call this method, go to the stable entry point, you always end up at the right place. The temporary entry point can be changed. This is the simple sort of scenario. It gets more complex when you have things like virtual method dispatch, because it has to decide which way to go, which implementation of the method, when you include interfaces. So the simplest scenario is an instance method on a class or a static method. Anything above that gets more complicated. Generics, we know in generics things are done differently. If you have a generic method that takes T, where T is an int or a double, that's shared code, that's individual code for those. So there's a different method implementation for the int version than the double version. Whereas if it takes T, where T is a reference type, it's shared code. So there's some tricks going on there. And it's using these stubs in different places. We just call the method, but the runtime figures this out for us. But something fundamentally changed around the .NET Core 2.0 timeframe. And there's a new feature came in. Has anyone heard of it? It's around Jit Compilation. It's also written on the bottom of the screen, I just realized. Sorry, it's on tier compilation, yeah. So tier compilation came in around .NET Core 2.1. It's not sort of a .NET standard thing, so I don't know how and when other runtimes might implement it, but it's in .NET Core. It was turned off by default in 2.1. I believe as of .NET Core 3, it'll be on by default. And that does something different. So the main issue with all of this is, and you can kind of see it in action here, is that the first time a method's called, it has to, the JIT has to do its job, right? And it's had this trade-off. Maybe if it could spend a long time, it could generate super efficient code so that if that method then gets called thousands of times a second, it's 2% faster, which obviously thousands of times a second makes a difference, right? But if it spends too long, it's blocking that method being called the first time. And maybe that method's only called once, and it's on the startup of your app, and it's between the user being able to first push a button or whatever it is. The JIT doesn't know that, right? So it has to kind of take a middle ground. It has to say, right, I'm going to do the best I can, but I don't want to do anything that takes too long. I can't do some of the optimizations that a C++ compiler that works, if you like, offline can do. So it's always been a bit limited by that. So what tiered compilation is, and it's something that's been around in Java and the JVM under the hotspot compiler for quite a while, but it's coming new to .NET, is that it will actually have a way that it can JIT the method more than once. So up to now in .NET Framework, the method's been JITted once, and that's it. That's then the native code that's run every single time from that point onwards. Tiered compilation kind of breaks that dependency and says, tell you what, the first time a method's called, we'll do the most basic thing. We'll just get some code out there as quick as possible. It'll obviously be correct. It'll be, we're not going to chuck anything out there, but it'll be the minimum, they call it minops, minimum optimization. And that doesn't do any of the clever tricks, but it means it can do it very quickly. So it helps startup time because it can JIT these methods quicker. Then, if that method is called lots of times, let's have another go at it, and let's do the maximum optimizations, or what we would have done before, or even more. Once it's got the two modes, it can then decide. And that's done in an asynchronous way. So once a method's been called enough times, okay, right, this method's important, it's on a hot path, whatever, it's called enough times, I'm going to, in the background, JIT this method again, I'm going to do the full optimizations. I can take, not as long as I want, but taking seconds when it's in the background asynchronously is not an issue. And it's worthwhile because if that method then goes on to be called a lot more times, the extra work the JIT can do there. So in terms of the main difference is there's another level of indirection after it's been JITted, and it goes through the pre-stub again, if you see with tiered compilation. And that pre-stub at the moment is basically a fairly simple counter, and it counts how many times the native code is actually called. And then when it gets to a certain point, it says, right, okay, this is a method I consider to be important. I'm going to ask the jitter on the background thread to do this. And then when it's finished, it switches in again, levels of indirection. It can just point. So now points to the optimized native code. It's still got the original native code because there's various reasons it might want to swap back to that, or it needs to have that for debugging and certain things like that. So it still has that native original code around that it did the first time. And once this is in there and they turn it on by default and they see that the main issue why they didn't turn it on by default in the first place is because there's this extra level of indirection. You're paying a little bit of a cost to go through this mechanism, even if you don't use it. So they're making sure they can make that as quick as possible or within acceptable limits. Because once you have this mechanism in, then there can be lots of reasons you might want to optimize code. If anyone knows, like, say, JVN and the hotspot compiler, one of the issues you get with virtual methods is if there's only one concrete implementation, of interface implementations, if there's only one class that implements an interface, you don't need to do the runtime lookup to say, right, it's class A or class B. You can just say, right, there's only one concrete instantiation. But the problem with that is if a type gets loaded later, a second class that also implements that interface, it has to turn that optimization off. .NET's not been able to do that. It's always had to allow for that second scenario. So this tiered compilation gives more benefits down the line. And I think we're going to see, once it's turned on and they know that it's not killing performance but helping performance, then they're going to start to use it in more things. And it means that the main promise is that the Jit compiler the second time around can do lots more things. It can be a lot more intelligent. It could potentially look at collecting other information along the way and things like that. So that's one of the few bits of this talk that is stuff around in .NET Core. So everything else. So we've talked about Jit compilation. At this point, our main method has been executed. But that's not quite everything else because we have these stubs. Because when we call out to console.writeline, that's not implemented in, that's calling out to the OS or the C++ library or wherever it is. It's something outside of the .NET runtime that it does to use that. And I sort of talked about it at the beginning, but this is, so to be clear what this is all the methods that were JITted in that application. This is something you can pull out from PerfView. I'm not entirely sure why these span helpers are here, actually. I need to figure that one out. But we can see our Hello World main there, and then these stubs. The way it works with pinvoke, you can see they end up in system.console. That's because we're calling console.writeline. And these are basically overload. You've got an int, you've got one with no int, you've got int32, sorry, an int. When it starts to call out to native methods, when you have, in effect, the DLL import attribute, behind the scenes, this is what it's doing. It's creating these stubs so that when you call that method, again, level of indirection, it actually goes via the stub. The stub does whatever housekeeping needs to be done before actually calling into the native method. And that is mostly, if we take the example of console.writeline, that'll be converting the string from a .NET managed string into whatever format the native library, and also making sure that the garbage collector doesn't move that string around while it's in that method, because the garbage collector expects to be able to move objects around as and when it wants. But once control passes out into native code, that's different. So it has to do some things around safety there, and then when that method returns, it checks the error code from the native method. If the native method is returning data back into the runtime, it needs to turn that, marshal that back from. So there's a few things there. So that's what's going on there. So we finally, after 50 odd minutes, walk through everything that the runtime does in that simple application. Just want a few caveats. So we never triggered the GC in that simple application. There's a few things that would happen if your application was a lot longer running. A few bits of the runtime, but 50 minutes is enough for anyone to listen about this stuff. But if you want more information, I blog about this sort of stuff. Lots of other people do, so that's the resources for learning .NET internals. There's a post I've done there that's other people's blogs on this. Tools if you want to explore this yourself, or techniques that I use when I'm exploring it if people are interested at that level. Other presentations and talks. There's quite a lot of people who are talking about .NET internals in different ways. The book of the runtime is book's a bit, anyway, it's markdown documents, it's text. But what it is written by the .NET runtime engineers for other .NET runtime engineers. So it's not an introductory text, shall we say, but what it is a real good explanation of why this stuff does what it is and how it works. A lot of my blog posts are basically, I read the page on there about some topic, stack walking, exception handling. I figure I know maybe 10% of it. I then go away, do a bit more research, look at the code, come back, and then by the time I think I can read that page and it makes sense to me, I figure I've probably learnt enough to write a blog post. So I try and write posts that might help people get into the runtime, book of the runtime book, but if you're into runtimes anyway, you might find it easier to get into. But it's not meant as an introductory. So that is it. Any questions? Yes?
Are there any sort of cross-platform or Mac tools for looking at this lower-level stuff, or is it still quite new that it will take time for some of that stuff to be?
Yeah, so the question was about tools for the looking at low-level stuff cross-platform. I mostly do all this on Windows, so I don't know for sure. But what I have seen is that clearly in the beginning, when they're porting to other runtimes, they're basically making the apps work, And it's only over time that the tooling has grown. So recently, that PerfView app I've showed you, clearly that's not going to be cross-platform. It's like WPF, the UI, but the collection part of the PerfView app is more cross-platform. So there's a perf script that will let you at least collect those events on a non-Windows OS, and then on a Windows OS you can analyze them. I think they're trying to make more tooling that doesn't require that, because even that level is maybe not great. But as far as I know, the profiling and debugging APIs are cross-platform okay, so that's why we're starting to see tools. But yeah, clearly we've had a heritage of being Windows only, so stuff doesn't catch up. But PerfView is probably the one that's, they try and, as they add new features, so like tiered compilation is now PerfView events, so they try and make sure that PerfView is the one place you can get this stuff, I think because they use it themselves. Whether there's going to be a cross-platform PerfView, I don't know, but at least at the moment you can collect it on other systems, so that's probably the best option for that stuff, PerfView, aside from, like we're pretty spoilt with, so you can debug through, I showed you the code in Visual Studio, you can debug through the runtime in Visual Studio. If you want to do the same, you have to use GDB and stuff like that, so I think you can use, I think the best option you have for debugging on other platforms is they made SOS work on GDB, so you've got the equivalent of WinDBG debugging. You can do that level on in terms of the runtime. For .NET code, it's slightly different. But does that? Just I suppose it's not up there as Windows. We've had 10 years of just being Windows only. So but they are. I know that they realise it's something that's missing, and I know what I've seen recently is they're making a lot more of the global tooling. So you can have things like, you've got .NET Run. They're going to have .NET Dump for making a memory dump, .NET Source for symbols, collecting the symbols, .NET Analyze. Those sorts. So I think it's under .NET/diagnostics as a repository where they're trying to make tooling built into the command line tooling to cover this. I think that's probably the other way they're going forward as well. Yeah. You get I didn't mention it, but you get for being the one who asked the question, you get a bonus. Free book.
Oh, fantastic. Thank you very much.
I've only got one, so sorry. Anyone else? I have got 3 t-shirts. Any other questions? Yes.
Yeah. Okay. Never mind. I will not ask.
You can have a t-shirt. Yeah.
One of the early phases where you set up the hosting thing. There's some I know about trusted platform assemblies. Is that mandatory in .NET Core? I mean, you know, the runtime configuration file and the deps file?
Yeah. So you're right, yeah, we saw it in that when I showed that demo. So I believe that's sort of the assemblies that I've not looked into how it treats it differently, but it's things like the assemblies that I think are mandatory have to be there. And I think they have special rules in that they can do stuff that more higher level assemblies can't. But generally, I think they equate to, what's the name of it in the .NET? You have the .NET Core app. You don't include them all. In the beginning of .NET Core, you had to include everything. You had to include system.strings, the DLL, all that. They bundled those up into the kind of meta packages. And I think the trusted platform assemblies roughly equate to those meta packages, which is like everything that's kind of mandatory. I don't know how it works in terms of security because we no longer have code access security and things like that. So I don't think it really affects, they can do that sort of thing.
What are the assemblies at your user profile .NUGET or the package?
NuGet, yeah.
What are those assemblies? They're also in the list because they also have to be loaded.
Yes, yeah. So
are those not in the trusted?
I think they would get added to the trusted platform assemblies list. Yeah. I think possibly it might be the distinction might be anything that's come from the runtime or the base class library is counted as trusted platform versus user code, as in what code we'd write ourselves. I think that might be the distinction between trusted platform assemblies and elsewhere. But yeah.
Also, the deps file, is that required by the runtime or is it just required if your code needs to dynamically load?
All that stuff is outside of the runtime. So that simple launcher app, Matt's CLR thing I showed you there, doesn't have any knowledge of that. That's all built into the .NET tooling, .NET Run and stuff like that. That handles that. At the end of the day, I think basically all that does is build up the trusted platforms assemblies list and passes it to the hosting API and says right here. So, but it goes through different routes, doesn't it? It picks up deps.json, it pulls down NuGet packages, it knows about dependencies, it knows about restoring, all that sort of stuff. It knows where to look for the different runtimes. But yeah, the runtime really doesn't know anything about that. The main way stuff is passed into the runtime is that trusted platform assemblies list, and then basically environment variables, settings, and GC configuration settings. The core of the hosting API is pretty simple. It's like, here's some DLLs, here's the fundamental modes like GC, workstation or server, and then off you go. That's it, yeah. Any other questions? Yes?
So, it's .NET Core because the app domain is effectively only one.
Yeah.
In terms of swapping assemblies, like unloading, I think it's coming in.
Yep.
Is that right?
Yes.
So, will that provide us the facility to sort of amend code?
Yes. So the question was around now that app domains have gone, one of the things that people would have done with them is using it as a way to load plugins and then at the end of it tear down the app domain and that go away, or things like that. So they have something called, is it application contexts? Sorry? Assembly load, that's it, thank you. Yeah, that's it. Assembly load context, and it's under the banner of unloadability. And the recent preview, the recent post about .NET Core 3 Preview 2 has a section on unloadability. And if you scroll down there, there's a design doc and a how-to doc. And for that scenario, yes, it's exactly what it's meant for. It's meant for, I'd like to load some DLLs in. I promise not to have any dependencies on those in code that's still there, because that's one of the issues, is once you have a link across, it can't tear down that if it knows you're storing it in a static field or whatever it is. But as long as you respect that, at the end of it, or actually not the end of it, the garbage collector, when it knows that, it will then clean up. So that unloadability. So I think they're doing stuff in that kind of way, more explicit, right? This is one scenario. This is actually what people were using app domains for. And a lot of the times, the proper isolation is not a thing. It's the fact you want to load some stuff, and at the end of it, you want to take it away. So they've gone down that route, yeah.
The mindset behind that, I think that's what we was trying on Java with PyTest and implementation testing. That swaps code out and in.
Oh, yeah. Yeah, because Java has the class loaders, doesn't it? And it can be, I don't think it's quite as configurable as that, but it's, I think it's starting to get that way where you can load. Sorry. Yeah, I don't think it's going to go. Because from what I understand in Java, you have different class loaders, and stuff that's loaded in one class loader can't see things in another. I don't think they're with. I haven't looked into the unloadability stuff loads to know, but I don't think it sort of prevents you calling across outside of it. It's more of when I'm done with these things, I want them to go away because of memory, and I don't want them hanging around, especially if they're DLLs on disk. You don't want to reference that sort of stuff. So, any more questions? No. Okay. Thank you very much. Please come and get T-shirts and stickers because I don't want to carry them.